Welcome back to programming a RISC-V emulator in a high-level language. In this session, we're going to try to finish up the work that we left off in the last time, where we were embarking on PC relative relocations. And I reviewed the episode and realized that I might have been skipping past a lot of material very quickly. So I wanted to give viewers a chance to catch the breath a little bit and review the material that we've covered so far. It turns out that PC relative relocations are kind of complex in comparison to the ones that we've seen so far. So let's dig in and start slowly and then see how far we get in this session. So we'll start with our sample program, which um, is right here in Visual Studio Code, and we'll just start from a blank slate. So what we're trying to illustrate today is global uh, pointers and how those work in an environment where your binary could be loaded anywhere in memory, at any address in memory to be more specific. So our little program will want to access some chunk of memory, say, and what we'll do is we'll create a little program that reads the length of a string and then puts that into a well-known register. And then the string will be located somewhere in memory. All right, so let's start writing some code. So the first thing we'll do is we'll create a main program, and the main program will uh, load the address of a string into a register. So that's the first thing that we want to do. And that register, because it's going to be the argument to the string length function, it needs to be an x10. In fact, before let's write this the way I would do this in C. So the main program would look like this, and inside of the main function, you would see a int length, or well, size t length equals strlen of some string Bob. All right, and then actually let's make this a variable then, because that's what we're trying to mimic. Elsewhere in the program, you would have a character array called Robert or Bob with a string Robert. Okay, so well, we would return size t. So let's just call this fn. It doesn't have to be main. It's just some function that returns a size t. So this is the function that we want to replicate. And so we also need to implement a strlen function. So let's write that. So it takes a string. And then what we do is we say while this string is not equal to 0, increment the string pointer, and then return, that's a size t. Another way to write this, of course, is instead of tracking two variables, we would just return the difference of the start position of the string. So we would say start equals str, and then str minus start. Okay, so if you're a C programmer, you recognize this. Fairly simple stuff. So how do we translate this into RISC-V machine language? Well, starting at the top, we are calling a function strlen, and we're passing in uh, the address of the buffer or array Bob in our register. So we need to put that into register x10. So in RISC-V assembly language, this is actually the address of the first byte of the Bob array. So we need to create a pointer to this array in memory. And this is the challenge. We don't know how to do this quite yet. So um, we will write what we would like to be able to do, which is to use this AIU PC instruction that we talked about yesterday. And recall that the reason why we have to do it this way is because the instructions on a RISC-V processor cannot fit a full 32-bit value, which is what we're trying to get into X10 here. X10 is a constant. It should be the address of Bob, but we don't know, we cannot fit a 32-bit quantity into uh, into an instruction. So we have to divide it up into two instructions. So the first instruction sets the upper half, and so what we do is we say in the variable x10, um, get me the high part of the address of Bob. And to indicate this, we say we'll ask the assembler. Let's get rid of this, by the way. We'll ask the assembler, hey, give me the upper half of of the PC relative relocation of Bob, like that. So what we're saying here is find the symbol Bob, and I want the high part of Bob's pointer. Okay, and then we have to accompany this with a add-I to x10. And here we went into a quirk. We want to say PC relative low, but very subtle point here. Instead of doing what you might expect and saying, give me the low part of Bob relative to the PC here, the issue is that the PC relative amount at this instruction will be different from the PC relative amount at this instruction, because this instruction is 4 bytes later in the instruction stream. So instead of specifying that we want the PC relative to be relative to Bob from this position, we instead say, assume that we know the position of a PC relative high relocation, which is this position here. Use whatever value of Bob you used, or whatever PC relative value you used for Bob in there over here. Well, and we'll see how this works in a minute. But now we have in X10 the high part of Bob and the low part of Bob as it was in this instruction. Those are now added together, and now we have a pointer in X10. So now we can call strlen. So let's do that. So we say jump and link strlen. And we discard the return value. Great. So now at the end, X10 will now have the return value of this function, which is going to be 6. Robert has 6 characters. So here we will then define the word 0, which is our lazy way of saying stop the program. Okay, great. So that is our main program. Now we write strlen. So strlen needs a label. Strlen, which is the length of a string. And so now, how do we implement this? Well, we need to hang on to the start of the string. So we need a scratch register to store that. Now it turns out that we have X11 and X12 are available. They're not being used for anything. So we can say um, add I into register 11, take the value of register 10, and add 0 to it, using our good old friend, the add I instruction. So now X11, we have original string pointer in X11. Nice. All right, so the next thing we want to do is start incrementing X10 and checking to see whether the value inside of x10 or pointed to by x10 is a 0 or not. But before we do that, we're going to jump to the test. So we'll do a jump to Stirlen loop head. All right, so the loop head will be somewhere here, like that. And so what do we want to do? Well, we want to check to see if the pointer that is in register 10 is pointing to a 0. So what we'll do is we'll say load byte unsigned. So read an unsigned byte and put it in register 12. And we're allowed to use register 12 because it's an unused input register to this function. And the first argument is going to be the source, which is R10, and then the offset is 0 because we're just reading the pointer directly. So now the byte that x10 is pointed to is in R12. Um, Now we check to see whether this is equal to 0. If it's not equal to 0, then this is a valid letter in, or this is a non-null character, which means we need to move to the next position in the string. So we'll do that by doing a branch if they're not equal to 0. So if register 12, the byte we just read, is not equal to register 0, which is always 0, then we need to go to a label called strlen loop body. And the loop body is over here, and the loop body will simply increment x10. So m dot add immediate x10, x10, 1, like this. So now we are ready for the next iteration of the loop. We check to see, we load the byte pointed to by the x10 register, check to see whether it is equal to the literal value 0, and if it is not, then we keep looping until we end. And once we've done all that, now what we want to do is take the current value of x10, which is going to be the location of the 0 byte, and then subtract from that pointer value the value that was at the start of the function, and that will be the result of this function. So we'll say subtract, and then we'll take the value, put the result in register 10 because that's our return register. Take the value of register 10, which is the pointer that's pointed to the end of the string, and subtract from that the value of the pointer at the beginning of the string that we saved at the beginning. That is the length of the string. And now we're done. So now we say jump and link register, and we want to discard the return and then take whatever was in R1 and 0. So that's our return to the caller. Finally, we have to define the string Bob. So let's create a label, and then we will define a string Robert. Here we go. So now we have a little program that does everything that we want, except we haven't implemented these relocation types. So let's jump in and do that. So this first PCRel high, we need to create a new relocation type for this because it's the high relocation type. So let's go to the relocation class and let's see if we already have. We don't have them, so we'll have a this is a PC relative high. and then PC relative low. So those are our two new relocation types that we need to create. And so this one will create such a relocation type. So we'll create we will, let's see, we will, well, let's just say emit relocation, current instruction pointer. The relocation type is PC relative high, and the name of the symbol is symbol. So now we've emitted that relocation. But now we have to pass on to the caller a dummy variable that it will bake into the instruction that we're generating. Because look back at the place where we use this. AIUPC needs some sort of number here. And so what we're going to give it is a 0 as a placeholder. Later, AIUPC, when the relocation gets resolved, that 0 will be replaced by the actual PC relative distance of Bob, or the high part of that PC relative distance. We don't have that value yet, though. So also we have to change AIUPC, or add a new overload to AIUPC so that it can accept a relocation instead. So let's go ahead and do that. Oh, and AIUPC doesn't even need the second parameter. So let's just get rid of that one. There we go. So now we have an error. That's because we don't have a PC relative low. So let's implement that. All right. So in this case, what we want is the PC relative low is this weird, unintuitive uh, version where we actually mention not the symbol that we want to be relative to, but we refer to the instruction that contains the relative instruction that we want to refer to. And the reason for that is that this instruction could be several bytes further down in the instruction stream, and so whatever PC relative high would compute here would not necessarily be the same thing as PC relative high would be several instructions downstream. So this relocation refer to the high part. And so the way it does that is by saying, well, my high part is whatever relocation you did 4 bytes back in this instruction. All right. So we'll just need to say like this. Well, the problem is, though, we need a symbol. We don't have a symbol. I mean, I guess we could force the programmer to, every time you do this maneuver, you would have to say label high instruction or something like that. But this becomes very, very tedious. So let us make the assembler do that work for us. So what we'll do is we'll create a synthetic symbol for every one of these backward references, so that we don't have to write that symbol ourselves. So the way we do that is we say um, add or generate symbol, and um, we'll take the current instruction pointer and add the instruction relative pointer, and that should give us a symbol value. And let's cast, actually, what is instr pointer? It's an unsigned integer. Let's cast all this to an unsigned integer. All right. So we need a function now that generates a new symbol, a unique symbol. And then now that we have that symbol, we can now then create a relocation for the relocation type PC relative low. And maybe if I spelled it correctly, relative. And then the name of the symbol. Nice. And then we again return a 0 as a placeholder. Now we need to implement generate symbol. So this is a function that generates a synthetic symbol. So what we'll do is we'll create these using a schema. So we'll say var, let's see, we'll have a variable called attempt. And so what we'll do is we'll attempt to create a symbol and repeat this until we find a value that is not already used. So we'll create a symbol name equals, and it will be an L for label, and then the address in hexadecimal, and then a suffix, which is going to be the attempt, like this. So that should give us a symbol name, and let's make that 8 characters wide for fun. So then we try to find the symbol. So we'll say, so if this does not exist, then we create it. Actually, the way this while loop works is, oh, we'll just do a for loop, an infinite for loop. Right. So if this symbol did not exist in the assembler, then would you create it? And we might as well use the function add symbol that we already had. Oh, we don't have an add symbol. Where do we create symbols? All right, so let's break this out and say, call this, let's call this add symbol. And then we can say add symbol name, like that. And then here, there we go. Oh, we need to return the newly created symbol. Good. All right, let's go back down here now. So in here, if the symbol does not exist, then we just create it. And then we return the symbol. Otherwise, we need to increment our attempt. And then we loop back. So this will loop repeatedly until we manage to create a unique symbol. So now we have a high relocation and a low relocation, both accessing their symbols. But the next thing we need to do now then is our linker needs to recognize these new symbols. So, or these new relocations. So we need to go to the linker and add a new case for these two relocation types. So start with relocation type PC relative high. So what is this supposed to do? Well, the mathematics get a little tricky. I found the following reference information in the RISC-V documentation for the linker and the relevant passages here. I don't want to go into too much detail about exactly how this computation is done, but it turns out that this relocation has a little wart that we have to add on a constant value before storing this into the requisite word. It's just a fact of life that this is how the RISC-V instruction set works. So we're going to just take the advice from this documentation and implement it in our linker. For further detail, if there's any interest, I can deep dive. But for now, I'm more interested in actually getting this relocation done. So how do I fix this? Well, um, we are going to follow the pattern. We're going to take the instruction, which, as you recall, right now has a 0 in the field where the high part of the pointer is supposed to be stored. And we're going to call ASM encoder encode. This will be, I think it's a J type, so it's a J displacement. But, and here's the thing, the displacement that we've computed needs to be adjusted by this number, 800 hexadecimal, in order to be correct. So what we're going to do is we're going to say displacement equals displacement plus hexadecimal 800, and then that needs to be right shifted by 12. So now I've followed the instructions in the manual. So now I can then take that value. Let's go back to the manual just to make sure that we are encoding the AIUPC instruction correctly. It's a flat, it's a U immediate, so we can use the encode U displacement. If we have one, we don't have one, so we'll just add one, like so. And then we break. All right, so let's see what a U displacement should look like. Well, it's going to be quite simple. It doesn't need to be broken apart into pieces like the other displacements need. So we'll just encode U displacement. So this is the displacement that we need to encode. And so if you look at the U-type instruction, it needs to be shifted over by 12 bits. That's it. So we will take the offset, convert it into an unsigned number, and then shift it 12 bits to the right. And that's it. No more work needs to be done. So that's our U displacement. Okay, great. And then after we've done that, we need to take the displacement or the re-encoded instruction, which now has the displacement, and then we write it back to memory. Ta-da! Actually, that's our ta-da. Great. For the low relocation, though, it becomes a little tricky. Recall that the low relocation, let's go back to the program to take a look at that. The low relocation takes a reference to an address where there is another relocation, and that is the relocation that we wish to use. So we have to keep track of every time we see one of these high relocations, we'll keep track of the address at which it occurs. And then when we need to resolve it, we will have to look it up by address to find the instruction address of the instruction that was relocated and then use that value for relocation. So we need a two-step resolution. So let's go back to the linker. And in the linker, what we'll do is when we create our relocations, we will also keep a dictionary that maps the address of the relocations to the value of that relocation. So let's do this the following way. We'll have a dictionary that maps addresses to relocations. And this will be PC high relocations. And we create this dictionary by taking the existing relocations and filter them so we only get the ones that the type is equal to relocation type PC relative high. And then we take those and we turn them into a dictionary where the key is the address. There we go. Now then, so when we encounter a PC relative low, what we need to do is first take, let's see what we need to do. Let's go back to the assembler. This symbol, we need to first resolve the symbol. That will give us the position, the address of the PC high. And then with that PC high, then we look up its relocation. And then once we have that relocation, we have the instruction that we need. So we need to first resolve the, and we should have resolved it here. So we need the symbol address. Okay, great. So symbol refers to the PC rel high relocated instruction. Okay, so then we have to say if, and then we have the PC relocations try get value symbol dot address. So out var PC high. So if we can't find a corresponding high relocation, then we have an error. So then we have to say unable to find matching PC relative high relocation. And we fail. So we'll just say break here. Otherwise, we have now the address of the, or now we have the high relocation. So now what we want to do is take that high relocation and extract the low bits. So how do we do that? We look at the instruction in the manual, and it's a simple extract the low 12 bits. So we'll take the displacement to be whatever value was in the the symbol address. So this would be, let me think about this for a second. I want to get this right. The displacement that we want is symbol. No, hold on. It's right. PC. So PC high refers to another symbol. That's the symbol that we actually care about. So PC high dot symbol name. And now we need to look that symbol up. And if we can't find that, then we also fail. So if we can't find that, then we already have a unknown symbol. Yep. Okay. Gets very hairy, this logic. Right. So now we have the actual symbol that we care about, which is the Bob symbol in this case. And so we want to say the displacement is the difference between this symbol and the address of the previous instruction, which was PC high dot address. And this is cast to an signed integer because this could be a negative displacement. And then what we do is we strip out the low bits. So we'll say uinster or equals asm encoder encode I displacement. Nice. And then we break. So how do we encode this? Well, it's very simple. We want to take the low 12 bits of this instruction. So we'll take the offset, cast it into a uint, and then keep the low 12 bits, which happens to be this value here. And then we need to shift it. Let's take a look at where that shift goes. The I instruction, where are they? Okay, so it's 20 bits. Okay, not 12. All right. Now I'm a little confused. No, that's not correct. The add I type, here we go. It's 12 bits starting at position 20. So we need to shift this number to the right 20 bits. That's our encoded offset. Good. And so, with all that done, we now have our encoded displacement. We OR that back into the instruction, updating it to the correct value, and then we write that to memory. And let's see here. We wanted the actual symbol address. There we go. So in theory, if all this goes well, we should now have the proper relocations for this. So you should probably write a unit test for this just to make sure that everything is hunky-dory. So let's go to the linker and create another little unit test that does the relocation of the upper and lower halves. And I'm going to call this relocate PC high, PC low, or PC relative high, PC relative low. And we'll start by creating a symbol, and we'll call it Bob, because why not? And then inside there, we're going to create a word of some random data. And then we're going to say AIUPC into register 10, the PC relative high value of Bob. Good. And then we need to do an add I of PC relative low of the previous instruction, which is -4. Okay, so now we have 1, 2, 3, 4, 16 bytes. This is what will end up happening. Ooh, hold on a second. Right, that's right. I'd forgotten this. We need to replicate what would have happened if we didn't use relocations. So in that case, we would see DW and the same value, I suppose. Yeah. But then we would see an AIUPC. And now what we expect is the value that the manual tells us we were supposed to compute. So this value, which is the symbol address, which is 0, and then minus the location of or the address of the relocation. But that's going to be 4. So we compute 0 minus 4, and then we need to add 800 hex to that. So that's, you know what? Let's bring up the calculator. So we start at address 0 in hexadecimal, and then we subtract 4, which gives us this mess, and then we add 800 hexadecimal, which gives us 7FC. So that's what we expect in the first byte. So 0xFC. And then in the low byte, we would see a -4, which is -4, just like that. Oh boy, this is going to be fun. It's an add I. Okay, full speed ahead. We try this, make sure that it passes our tests. And so what we want to do now is verify that the word in this address, those two matches. And then we also want to assert that the word at address 8 matches. Okay. All right. Let's give this a whirl. We will run our tests, and we expect, haha, do you think it will work the first time? I don't think it will, but I'm pessimistic. Oh my goodness, it actually ran correctly the first time. Well, will our little program run? So let's go back to the main program. So the idea is that we're going to call string length on the string Robert, and that should give us the value 6 in register 10. So at the end of this little program, when we finish and we execute it, we want to print out the result, which will be in register 10. We don't need to initialize any of the registers. All right, let's give this a try. Oh, this will be exciting. Now we get a 0. So our program did not work. Um, okay, great. So why didn't it work? Um, let's see. What we could do, of course, is a single step through this. It's going to be tedious because we don't really have a debugger for our machine language. But what we'll do is we'll go to the emulator, and what we'll do is we will display the instruction that we're executing along with some values in registers that might be of interest. And lacking a real debugger, we'll just make do with a primitive one. So we'll say console write line, and what we'll do is we'll put the current address where we are, and then we will dump the values of x10, x11, and x12. And so to do that, we say iptr, and then registers of 10, 11, and 12. All right, so let's run our program. Oh, okay, so we ended up in an infinite loop. We have a watchdog timer expired warning here. So somewhere in our logic, we went wrong. Look at that loop spinning and spinning and spinning and spinning. Okay, so let's start at the beginning and see what actually happens. So the first instruction here is supposed to initialize x10 with a pointer to Bob. And clearly that is not working right. All right. So let's single step then. We'll have to do this slowly to make sure that the pointer values are being correctly initialized. So what's the first instruction that we're going to execute? Let's find out. So this should be the AUIPC. Here's our AUIPC. The destination should be 10. Good. And the immediate value is a 0. So it looks like our relocation did not get applied. Oh, wait a minute. No, let's not jump to conclusions. We are at address 0, and the relocation is a small positive distance away from us, so we should be okay. All right, so we'll accept that for now. Then the next instruction is an add I, and the add I instruction will take the immediate value. Now this is the problem. Source 1 value should not have been 0. That should have been some other value. Okay, so Here's the problem. So let's go back to our program, make sure that we're referring to Bob. Yes. Okay. So let's go to our relocation because that's very likely where the problem is, at our low relocation. Because we expect to see a small positive offset for the string Bob. Okay, so here we go. So we are now trying to look up um, ba, 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 ba. That's going to fail. We are looking up the wrong thing. Did we not record the address when we? Okay, let's take a look. So go to the assembler and look at PC relative low. We generated a symbol, or we should have at least. Let's make sure that that actually gets created. So let's run that again. So here we go. We create our symbol whose name is L000. Yeah, that makes sense. Okay, good. Now we have a symbol. We come back and then we say, please emit a relocation of type PC relative low using the symbol name and make that relocation at my address 4. Great. So there should be a symbol, and in our symbols collection there should be a symbol called 0. Yeah, there it is. And it is located at address. Oh, that's the wrong address. It should be instruction pointer 4 minus 4. That symbol should have been generated at address 0. So there's something wrong with generate symbol. Let's do this again. Put a breakpoint here. Try running that again. Okay, so here's our symbol generation. We go inside. Our symbol is at address 0. That is correct. And our relocation is going to be at instruction pointer, which is 4. So that is also correct. So those two pieces are correct. Then when we resolve the relocation, we say, find me a high relocation at the address. How did, where did symbol come from? This is from my relocation. Okay, I'm seeing ghosts. Let's see if I can figure this out. Symbol value is 0. Good. And when I emit the relocation, it's a relocation for the symbol whose name is that. My current place, the place where I want the relocation to happen, is 4, and the relocation type is low, and the symbol name is 0. What does symbols look like? Just a single value. That's not correct. The value of the symbol is wrong. And here's the reason why. Okay. Do over. All right, let's try this again. So now, when we get to the relocation, the symbol address is 0. Perfect. So that should give us the relocation that we need. The relocation will then have a symbol name called Bob. Now we have Bob. We take the difference between the address of uh, Bob and the address of the PC high instruction. That should be a displacement 44, and then we write that displacement. Okay, good. Relocation should be okay now. So now let's execute that. Let's execute that. Why am I not seeing the register values? Oh, there it is. So X10 now has the value 44, which is 2C hexadecimal. And that should be the address of Bob. Let's verify that by executing the jump or the call. And so now we're going to read the value. First, we copy the value into 2C, which is the X11, the spare register. And then the next thing we're going to do is we're going to do a little jump. There's our jump. And now we're going to compare, we're going to load the value at that location into X12. And that is a lowercase b. And that's not going to be equal to 0. So we jump back and we increment the pointer now to 2D. And then we load another byte. That's a lowercase o. That's the lowercase b again. And finally, no, sorry, that was an R. O, B. That's an E. This is an R. This is a T. And there's a terminating null. So if our logic is correct now, the loop should break out. And now we compute the difference between the starting value of the pointer, which was stored in X11, compared to the ending value, which is 32, and we get the number 6. We can remove the breakpoint now. I have confidence that, oh, what are we returning? I spoke too soon. Where is this 4-6 coming from? We're not, oh, we still are looping. We never leave the loop. Well, that's interesting. So, all right, let's put the breakpoint back. Why is the loop not terminating? Let's go. So here we go. We're setting up the letters O, B, E, R, and there's T, and now there's a terminating null. The terminating null puts the value 6 into the return register, and now we should be able to return back to our caller. End up at address 0. Are we returning correctly? Let's take a look at our program to make sure. We're doing a jump and link. Is there something broken with jump and link? Unlikely, and we're not modifying it. Oh dear. There we go. We were writing the return address to register 0, which throws it away. So that's not very useful. Let's try that again. Let's get rid of some of these. And there, finally, is the end result. So we now have written a linker that handles the new relocation types for PC relative addressing. And so at this point, our assembler is pretty much complete. You can assemble any significant RISC-V program and support most of the interesting addressing modes that we would ever need to do, and most of the relocations that we would need to use to write a real program. In our next session, we're going to talk about other parts of the emulator. We're going to talk about memory, which has been long neglected. For the time being, though, I'm going to say goodbye for this time. Hope you enjoyed this, watching me struggle through all the bugs, and talk to you next time. Arrivederci.